Tutto mi sei anch'io, un palazzo che insegniamo. Fa piacere vedere.
So national failure rate were by Maistro, and he has added mathematics here in Padua and then explored in computer science at our department, and now she is in track assistant professor at the University of Copenhagen. She works in information retrieval, as she has from the course, and she works on evaluation, visibility, visibility, recommended systems, and closer to the form of the course today, this information has user model and machine that apply to the system. She has organized several scientific events, and through which she will be chair of CIR 2025 in Padua next summer. So my name is Maistro. Thank you very much for coming.
Thank you, Nicola, for the nice presentation and inviting me to give a talk like here where I started my education. So happy to be here. If you have any questions, just feel free to raise your hands and ask. First of all, I want to say thanks to my co-authors. So here is a bunch of people involved in the papers I will present today. And as you might have guessed from the title, the topic today is how to evaluate field relevance. So I haven't seen the evaluation lecture from Nicola, of course, but I expect it focus a lot on relevance, which can be binary or multigraded. But actually, we know that relevance can be multidimensional, can be dynamic, and is in general something complex and subjective. So it depends a lot on the user. So we might want to consider other aspects on top of relevance, not only technicality, but there are other important aspects or dimensions we might want to consider. And to give you an example here, some people talk about an information nutrition label for news or any type of documents you can find on the web, where it's not just about relevance, but for example, how much facts you have, how much of opinion, controversy, and so on. And this gives to the user a kind of sense of what is the user looking at. And this calls for some solutions. So how do we deal with all these criteria when we evaluate? And why is this important? Well, there is an example here of a query, can smoking prevent COVID-19? This is an actual topic that we use to track. And if you search for documents based on this query, actually you find out that you can find some documents that says, okay, smoking is not healthy, does not prevent COVID-19. Other which are more like, oh, there is this new evidence that maybe smoking can prevent COVID-19. And at this point, maybe the user cannot distinguish between what's correct and incorrect. And what we want to do when we evaluate search engine is hopefully try to get rid or at least not promote misinformation or information that is not correct. And we want to promote on the other side credible and correct information. So we need to account for these aspects in the evaluation. Another case that we will see today, there is a lot about generative AI so far. And for example, it has been shown that there is a lot of bias there. So here they generated some images, and what turned out was that many of the female represented or generated by different AI models that were like old women with wrinkles and so on, while men were like beautiful looking and young. So somehow there is some bias out there in the data. And when it comes to ranking, whether it is recommendation or search, bias can show up. So for example, some years ago, Amazon was using this tool to automatically basically select or recommend candidates for jobs. It turns out female candidates were not recommended or not as much as male candidates, and that's because the algorithm was trained on historical data where most of the software developer positions were applied and assigned to male candidates. And the same it goes for Google, where actually has been shown to be biased towards like men when showing high paid or prestigious job ads. So again, how do we want to evaluate these systems? Maybe relevance alone is not enough, and maybe we need to worry a bit about fairness. So what we will see today is the two main topics. So the first part of this talk will cover evaluation with multiple aspects. So when we consider, as I said, not only relevance, but for example, correctness and credibility. And here we will have a look at the state of the art, as well as some novel approaches that we propose and experiments to evaluate these approaches. And then we move to fairness evaluation. We will have a look at different definitions of fairness and again limitations and experimental evaluation of these measures. And we conclude with wrap up at the end. So to focus on multi-aspect evaluation, let's assume you have a query. It can be like vitamin D and COVID-19. And then these are the results we get. And now, as I said before, you want the results to be relevant, so you can assign a relevance label, but that might not be enough to prevent, for example, misinformation. So you want to assign another label that tells you which result is correct or not. And the main question is, how do we account for these two labels when we want to evaluate a record quiz? So in the state of the art, what has been done, usually you have one aspect, let's say it's relevance, and then you compute any IR evaluation measures for relevance. So this can be like average precision or LLCC or any other measure you have seen in this course. And this is just completely considering relevance. And then let's say you have a second aspect, and you do the same. So this measure can be the same, but it can also be like that you have two different measures, one for relevance and one for correctness. And then what happens is that you aggregate them. So you take the score from coming from relevance, the score coming from correctness, and you take, for example, the average. So there are three main measures out there in the state of the art for this case. The first one, it's convex aggregated measure. With me, it's like an average. The second one is harmonic average, and it's basically the same as the last one. So how do they work? This is HAM, so you have a ranking with multiple labels for each document. And then, as I said, for each aspect, it can be relevance or correctness. You'll compute a score and then just take a weighted average, where this is a parameter that you can decide depending on how much weight you want to give to each aspect. And similarly for it's the same idea, but it's just that you take the harmonic mean instead of the mean, and again, you have this parameter that assigns a weight for each aspect. And again, you can use any IR evaluation measure when you do the harmonic mean. What's the problem with this approach? Well, here we have an example of CAM and MN, where we have different topics. This is the track, decision track, or have misinformation track. And what we did, well, now we tried to generate the ideal ranking, so the best possible ranking for the documents that we will have for this topic. You can think about this exactly as the ideal ranking of NPCC. It's just that in this case we have multiple labels. There is no single ideal ranking. We will see later why, but the reason is because we have these labels coming from these different aspects. So we try to generate different types of ideal rankings with strategies that are somehow reasonable. And then we compute the scores for this ideal ranking. And what you can see is that these scores are somehow spread in the range of these measures, 0, 1. And for many topics, there is no ideal ranking that is able to reach the perfect score. So what happens is in the first, let's say, practical scenario is that you have these measures common and that do not range anymore in 0, 1, but they range in 0 something. And you don't know exactly what is the upper bound. So it works whenever you want to compare different rankings, but the interpretation of the scores is a bit harder. And again, very often what is reported is the average across all topics, and this it's hard to interpret if you have different ranges for each topic. So the second approach that we have in the state of the art, again, we assume this example that we have two dimensions or aspects, but now the application is at the level of labels, not at the level of scores. So you somehow need to aggregate these labels depending on the different strategies, and then just compute a single measure on the aggregated labels. And again, this single measure can be any IR measure, state-of-the-art measure, as average procedure, or MCC. So there are many measures in this category, and also our solution is in this category. All these measures, like alpha and DCG, deals for relevance and diversity. This is called Q test, normalized relevance, novelty, and user effort, and so on. So one of the problems in this category is that all these measures they are defined for a specific context. So a specific set of aspects. And again, for some of these measures, it's very hard to define what is the ideal ranking. So what is the best way which I can sort my documents? So in practice, what happens if we try to take some of these measures and use them anyway with the aspects that we have? So we use this measure, normalized local rank error, to evaluate again runs from the decision track. So here you have all the ranks, and these are the distribution of scores across topics. So the first thing you might notice is that all the scores are squeezed towards 1. So again, this measure is supposed to range 0, 1, where 1 is the best score. But reality said that it goes from 0.95 to 1. And this is because of the definition of the measure that was considering only 2 aspects. When here we consider 3 aspects, and the measure somehow explodes in the number of combinations that needs to be considered. And the other issue that we have over there is that all those ranks, they're not the same ranks. They're not sometimes even from the same group, but they are equally good for this measure. So the measure is not really distinguished among these ranks. Another problem we might have in this family of measures, so we have compatibility. This is a measure that actually assumes that you define a preference order among the labels that you have, and then compute rank bias overlap between the ideal ranking that you can get from this preference order and the actual ranking that you have. Now the problem is that when you have, like for example, 3 aspects useful for rightness and credibility, what you can see is you have different combinations, and the question is how to define this preference order. So actually, you can end up having a lot of combinations and a lot of decisions to make. So, what is the core problem here? So why is it challenging to evaluate with multiple aspects? So let's say that we have 2 aspects. Again, it's relevance and correctness. And then we have these grades for relevance, so highly relevant, fairly relevant, marginally relevant, and non-relevant. These are sorted. And also correct, partially correct, or not correct. Now, if we have 2 documents, in this example, one is highly relevant and correct. The second one is still correct, but it's marginally relevant. Then it's kind of easy to say, okay, this document is better, the one that we choose, because they have the same level of correctness, but the one is more relevant. So I want to have the one ranked higher. Now, if we have a third document which is highly relevant, but partially correct, again, if I compare the 1 and 3, and I want to have the 1 ranked higher because same level of relevance, but that's correct. But now when it comes to the 2 and the 3, I don't know what to prefer. So now the problem is, do I want a document which is more relevant or which is more correct? So a decision has to be made in this case. And when you compute aggregation measures like average or harmonic averages, then it's not clear what is the decision here. So we formalize the problem. So let's say that we have n different aspects, for example, relevant and correctness. And for each aspect, we assume that we have a set of labels, and we have kind of order relation among the labels. So the same as you can sort relevant labels from non-relevant to highly relevant. Then we also assume that for each document and topic, we have a grammatic function that basically for each document tells you, okay, this is the label for the first aspect, the second aspect, and so on. And what we call the equivocal order. So it's the same order that I showed you in the previous slide. So if one document has better labels for all aspects, better or equal, then lower or equal than the other document first, then the first is somehow considered better. Now, this is a partial order, and we can have documents that are not comparable. So where we cannot conclude whether B1 or D should be ranked higher. And this is the same example as before with each one. So what we propose to kind of tidy up a bit evaluation with multiple aspects is to use a 3 steps approach, where in the first step we embed all the labels in a geometrical space. We use the Euclidean space. Then we complete the distance function, and based on this function, we'll define an order relation. And the last step is kind of a weight function that, based on the distance, assigns some weight. And then once we use this whole approach to aggregate labels, then we can compute any other measure on top of this. So I will give you an example to show how it works. See again that we have relevance and correctness. Now I replace the labels with numbers because this is an example of how you can embed these labels in an Euclidean space. And we assume we have 4 labels for relevance and 3 for correctness. Now we also assume that these 2 points, for example, do not exist, because if you have a document that's not relevant, it's also not correct, or it doesn't make any sense to see if it's correct or not. And then what you can do, so you say, okay, this is the best possible document I can have, because it's the most relevant and most correct. And I want to look at the other labels and compute the distance. Now, here we use the Manhattan distance. And these blue lines are the equivalence classes. Basically, all these labels has defined by multi-dimensional labels with different aspects are at the same distance from this best label here. So once you have these equivalence classes, then the idea is to define functions that map each class of labels to a single weight. It's the same idea that you have when in standard evaluation you take the labels and you map them to some weight. So to formalize a bit our idea, the first step, as I said, is the embedding function that maps each label in your geometrical space, and then you define the best label. So you can find the label that has the maximum for all aspects. And then what you want to do is to compute the distance. So the closer one multi-dimensional label to this maximum, the better the document. And we tried different distance functions. And once you have the distance function, basically this defines the weight order, where you will have 2 multi-dimensional labels that can be at the same distance from the best label as in this case. And then we consider them as in the same, well, they are in the same equivalence class, so we will map them to the same weight. In our experiments, we tried 3 different classes, so Euclidean, Manhattan, and exhibition. Sorry, 3 different distance functions. For each, what you can see here in blue are the equivalence classes, so labels that are at the same distance to the best possible. And then, as a last step, as I said before, once you have this equivalence class, you want to map them to an integer number. And this is compute any higher measure. So what we did is put this requirement on the weight function that we use, so that we preserve basically the order that's defined by the distance function. So this is the order defined by distance. So distance is the best label. And we want a weight function to preserve this order. At the very end, what do we do when we compute the final score? Well, it's basically a composition of the IR measure you want to compute and this weight function that's based on all the previous steps. So if you follow all these steps as described, what happens is that the distance orders, the order that we define based on the distance function, preserve what I called before the unequivocal order. So you're sure that all the comparisons that we kind of easy comparisons that we discussed before, they will be the same once you go through all the 3 steps. Then your distance order will make a decision on those multi-aspect labels that were kind of not comparable. And you can find, I will not go through the proof. So how is it used in practice? You have an example here. So we have here again relevance and correctness on the same scale. We consider like different embeddings and different distance functions. And what happens is that here we assign the same range for relevance and correctness. Here we use the same step, so all the labels have 1 step size. And here we increase correctness to be in the range double as relevance. And in red, what I have highlighted, these are the documents for the labels that represent somehow misinformation, because these are relevant and not correct. So these are the documents you really would like to not promote by your system. And then you can see that the more you increase the range of correctness labels, the more you push your misinformation, let's say, towards the end. So we evaluated this approach with different data sets. So these are the data sets that we consider. Yes.
When we need the assumption that not relevant documents not correct,
Yes.
simply the proof somewhere.
No. So the proof is independent of the type of aspects and so on. This is because it was like a practical example, you don't have to assume that.
Okay.
So it might make sense for other aspects. But in general, for retrieval or recommendation, because you want to recognize something relevant.
I understand that's about.
Yeah. Then, but the proof and everything else works without that assumption. Any other questions? So yeah, so these are the data sets that we considered with the number of ranks that were considered and the aspects. So we had 10 different tracks in track, more than 400 ranks. The aspects, some of them we generated them. So for example, popularity and its commoness, based on page rank score and what was found ranking. Others were annotated by humans. And as baselines, we considered the 2 ways to aggregate the scores. So CAM is average and then it's harmonic average. We didn't consider other measures because, as I showed at the beginning, they depend on the type of aspects that you have. So we do not compute them. We had all the 3 different functions, ingredient, and intention. And as IR measure, we consider LST, which is graded and average precision. That's binary. And we had embeddings with unique 1 for each aspect. So the first analysis we did was Kendall canvas style correlation. So the idea is that we have rankings of systems generated by different measures, and we want to see how similar they are. So when we computed our measures, we saw that Euclidean and Manhattan, they get very high correlation. This makes sense. And it also makes sense for this to be perfectly correlated somehow when we use average precision because of the mapping of all the labels to binary cases. When we compared with state of the art, what we saw is somehow that using Euclidean or Manhattan distance resulted in some sort of high correlation, but again, it's not the same as the average. While the temperature distance is more similar, let's say, to the harmonic average. And again, this made somehow sense because temperature is quite strict. You can think about this as a measure, because whenever, for example, one aspect is 0, then everything is flattened there. And then somehow works similarly because it's a weighted average, harmonic average. Another analysis we did was discriminative power. This is a test somehow to assess how good the measures are in discriminating across systems. And what we saw is 16 cases out of 20. Manhattan was the best, followed by Euclidean.
Can you explain what you mean by the best? So how will you evaluate this discriminative power?
Yeah, so basically, what these are, the best means that whenever they consider two different rankings, they are somehow able to discriminate between them with a statistical test, so that there is significant difference between them. So now, to be honest, I don't remember exactly the details of how the test works, but it generates multiple comparisons with bootstraps across different pairs of rankings, and then every time measures if the not look at the p-value and see if there is statistical difference. And the hypothesis is that there should be. So one thing we notice here is that, like here, for example, we are very low, and this is again the Celsius case or the distance. And again, if you remember, like this, what I was telling you before, that this area of Celsius being like the street, and this is because you are like all these dots, somehow they are in the same class. So all these labels and documents that are there are considered as equivalent. So it's not very good in discriminating for some specific data set, because these data sets were also the data set that had some very high sparsity for some labels. So in many cases, you have a multi-aspect label with one mass that is 0. And the last experiment we did was to look at the documents that are actually returned when we use these measures to evaluate rankings. So what we did here is for each, we use each measure to select the best rank for each topic, track, and year. And then we look at the top K documents that are returned in the rank. So here K goes to from 1 to 5, for example. And then we counted how many documents had zero aspect label. So the idea behind this analysis was that we wanted to limit trash out of the top page. Right here, we look at the average per label with the idea that we want the labels to be like as high as possible across the assay. And again, what we saw is that basically Toma based on Manhattan, it's very good. So to summarize a bit about this part, so what are some of the limitations we have for this approach? Well, first is based on arbitrary choices. So for example, the embedding distance or the weight functions, and it's not clear what is the impact of, or exactly what is the impact of this choice. So this is topic for future work. Also, somehow when we do the embedding function, we map what is an interval ratio scale, sorry, a nominal or ordinal scale to an interval ratio scale, and again, it's not clear what are the implications of this. There are also other things about the interactions between different aspects or documents not being modeled by its approach, and we will see about its fairness. So, for example, we cannot do fairness evaluation with this approach because we need to assume that all aspects are somehow independent or can be assessed independently to some extent, independently of the ranking. I mean, so in isolation when you only have a single document. And finally, it's true that this works for any number of aspects, but the more aspects you have and the more grades you have for each aspect, the more equivalence classes that you have. So again, maybe it's not a good idea to use game-based measures for example, MSH on top of this approach. So to wrap up, we have this approach that works for any different type of aspect. We can have different grade for each aspect, and it allows also. It's true that we have a lot of decisions to make, but also this allows for some trade-offs. So if we want to assign more weight to one aspect or the other, can work with existing IR measure and we saw that empirically as some advantages. So if there are no questions, I move to evaluation. Yes?
Does it make sense or is it possible in your experiments you compare the different baselines with a comparison between other cases when you have a ground to ranking, maybe you can compare measures, or is it impossible?
No, that's part of the problem because so usually when it's a single aspect, like for example relevance, you just rank your documents based on relevance, right? But when it is multi-aspect, then you can have these documents that you don't know how to rank. So you have to make a decision, and that's what we do for with Toma. Now we couldn't evaluate this for the other measures because they don't. So it could have been like an unfair comparison. Somehow we show that theoretically it might be more correct to use Toma because you generate the ground truth and then you just tell me, okay, this is the ground truth I want, the ranking that I want, and then my measure will assess for the similarity of my ranking to this ground truth. While for these averages, you don't know what is the ground truth, and you just have a score that puts out. Yeah.
So back to this question. Practice, how do I know and then I have a good framework with matrix. So now, ask me some very complicated things.
Yeah.
Otherwise, it's not a mathematical issue.
That's a good, like, I think that's one of the core problems of IR regulation, that it's not really like, we don't really have a real ground truth. So we have some approximations of the ground truth, as like Thomas does, but it's not like, I don't know, when you have to measure the height of a tree, that you kind of have a physical property that you can measure. Here, the ground truth is maybe the user satisfaction at the very end. And the way we approximate this is by asking, okay, is this relevant or not? And then also, if you want to consider other aspects. But that's also why we have so many measures defined for evaluation and a lot of discussions going on. And this is basically offline evaluation, which is done before deploying a system. And then usually when the system is online, what it is online evaluation with real users, and maybe even before putting the system online, try out with real user and ask them how is the experience and so on, and all the A/B testing cases.
Is it conceivable to have some parameters that can adjust the reaction of the users?
Yeah, yeah. So a lot of evaluation in industry is done through A/B testing, basically, where they have two systems running online at the same time, and then based on how the user clicks or behaves, or many measures that define, like engagement and retention and conversion rate, and they really have a lot of options. They actually really try to understand if the user is satisfied or not. Then there are some studies that try to make the link between what we do offline and what we do online. It's really hard, and it's not generalizable. So in principle, you do it offline first to make sure that things are as expected. And if you have good scores offline, then you move online. Any other questions? Good. So, what is this thing called fairness? Well, fairness, there is a lot of fairness in machine learning. You might have heard about the ProPublica, for example, where they analyzed the system that basically decided on whether these people had good reason or not. And turned out that the system was very biased against race. Now, when it comes, and this is usually like the standard classification problem. When it comes to fairness with rankings, we have different challenges. So here it's not classification, so it's not like, okay, I have a sample and item, I want to decide if it's +1 or 0. It can be, for example, a document, I have to decide if it's relevant or not. Here I want to generate ranking. And what are the main differences here? Well, the seals are not independent, as it happens for classification, but there is dependencies across documents in the ranking. And that is why, for example, like before, we cannot use SOMA for evaluate fairness, because you need to take the full ranking into consideration, not document by document. You cannot assign a fairness level to a single document. Decisions are repeated over time. Usually you have, you do like a search multiple times per day. They personalize, because nowadays the systems learn from your past interactions. Relevance is very subjective. as I was saying at the beginning, it's very hard to know when a document is relevant or not. And both stakeholders involved. So it's not only like the user that search, but it's also like who are the providers of the content online. So if you could search on Amazon, for example, who are the vendors or the producers of these items? And usually in fairness, we have two main distinctions. One is group fairness and the other one is individual fairness. So in group fairness, you have two groups. This can be based on gender, it can be based on race, age, any attribute that makes sense for your problem. And the idea is I have users in these two different groups, but I want the system to treat them in the same way. So I don't want the system to generate a bias, for example, as I showed you at the beginning, towards female that are applying for software engineering jobs. The other case is individual fairness. So I don't really care about the specific attributes of the users. So it can be gender, age, or whatever. But I want the system to treat in a similar way similar users. So now there is a conflict between these two. So it has been proven in the context of classification that if you achieve group fairness, you cannot get individual fairness or the other way around. But in ranking, it's still like up to discussion. So it's not being formally proven. The other distinction that is made is another type of level, which is consumer versus item. So you might want the system to be fair to your user. So again, if it's a group fairness, you want the female group to be treated equally to all the other gender groups. But you might want your system to be fair to the items. So it can be, if you are on Amazon, different items that are from the same provider. Then this group of items actually gets more exposure than all the other groups. So you don't want a provider, for example, to be overrepresented in your searches. And this might be because there are, I don't know, new providers, new to the market. You want to give them equal opportunities as other providers that are in the market for more time. And again, there is a conflict between consumer and item side. So, as we proven that you cannot achieve both of them, at least you cannot optimize both of them simultaneously, you need to find a trade-off. So what we have out there is around 60 different definitions of fairness for rankings that resulted in more than 45 definitions of measures for them. And many papers actually use only one measure. So one of the problems is how you choose between these, among all these measures, which one to use. And there are many taxonomies out there about fairness definitions. So one distinction is between process and outcome. So for example, if you want the process, the algorithm by itself to be fair in the way the algorithm works, or if you want actually outcome to be fair. So when you compute any information retrieval measure like MCP and so on, you want the score to be fair. And then again, you can have individual versus group fairness, and within this group, you can have different variations, like whether you compare the scores, whether you compare the distributions, and so on. The main, let's say, dimensions that we have across all these definitions are summarized here. So one thing is benefits. If you use exposure or effectiveness. So exposure is how much visibility you give somehow to documents, and effectiveness is related to relevance. Then you can have different definitions that differ on the stakeholders, as I said, like user side or consumer side versus items providers. In partition, if you go to two groups, many groups, villas, and so on. How you define exposure, if it's a set-based, rank-based, and so on. And the criteria type. So if it's proportionality, sign, utility, and comparison of distributions, and so on. Now, what we did, we focus on individual item fairness. And why that? Well, because it's kind of important for ranking because it's related to item discovery and somehow preventing popularity bias. If your system is fair from the item side, then what you expect is to have more diverse documents. It does not require knowledge of sensitive attributes. Most of the time, you don't need to define groups, so you don't need to have a gender, age, or any other attributes that are not easy to collect. Group fairness suffers from intersectionality or gerrymandering, which means that intersectionality is the problem when you have multiple groups and you want to be fair to these groups based on different attributes, then results hard to combine all these all fairness across all different types of groups you can define. And gerrymandering is when basically you can have group fairness, but doesn't mean that your algorithm is actually fair within a group. So, for example, you can have a good balance between different genders, but it doesn't mean that within a specific gender, like for example female, you are fair across all the users there. Also, in some cases, individual item fairness might be group fairness, but not the opposite. Even though, as before, there is still like a lot of discussion going on here. And it's usually provides broader view because you compare individuals and not just groups based on a single attribute. So which type of definitions do we have for individual item fairness? Well, they are based usually on exposure. As I said before, this is usually measured in terms how many times an item or a document appears within the top 8 results, and considers sometimes the rank position, sometimes it's just the top page with a set based. And the other aspect that can be considered is relevance. So whether the result is relevant or not, or whether the user interacted, for example, with the result or not. And then even these two ingredients, individual item fairness usually is measured as either all items having equal exposure, so equal opportunities to all documents, or same as one, but subject to relevance. So all items that are relevant, they need to have equal exposure. Now, I'll prepare an example here. So let's say that we have 4 items in our data set, and we just show to the user 2 items. This is user 1 and user 2. They get the same exact ranking, so only 2 items are exposed here. And this we have phase 2, where we have again the same 2 users, but now we expose all the items in the data set. So now consider that we only look at exposure, so we don't care like which item is relevant or not. So what do you think is the most fair case? So maybe you can raise your hand if you think that case 1 is the most fair or case 2 is the most fair. So who thinks it's case 1? Case 2? Okay, majority case 2. So case 2 is more fair than case 1. More items in the data set are exposed. But there are some cases where these 2 are considered equally fair. And this depends on the definition of fairness. And this is because like these items they have the same exposure across users. So they don't care that 2 items are not exposed at all, but they just care about what is exposed to the user. So now, same example as before, but now we have definition with exposure and relevance. So we assume that in case 1, all the items, all the users receive relevant items, while in case 2, user 1 actually gets relevant items, while user 2 gets only non-relevant items. So now the question is, which case is more fair? So who thinks it's case 1? Okay, some. Case 2? No one. So again, case 1 is more fair than case 2 because more relevant items are exposed. But again, this is a measure. So most measures are within this framework, but there might be cases where we go that way. So this was just to give you an idea of like what's out there. And because we have so many measures and so many cases, we took all the 9 different fairness measures for individual item fairness that are available in the state of the art and kind of makes sense to use for evaluation. And we tried to analyze their theoretical properties. So we find 5 kind of limitations. 3 were defined by us for the first times. 3 were 2 were already there, but they were not like globally defined. And here, what you can see is like those are limitations that we identified and we solved now. So we could correct the measure to work a bit better. These are limitations that cannot be solved for different reasons. What you can see from this overview is there are no measures without limitations, fortunately. And the type of limitations that we have, like for example, the non-realizability, is very similar to what we were looking before with the trauma approach. So what happens here is that because you don't have a real ground truth, or you don't know what is the ideal ranking, you don't know what is the range of these measures. So you don't know if they go from 0 to 1, or what is the upper and lower bound, and sometimes it's not even possible to compute them. So we evaluate also these measures from an experimental point of view. So we had 2 different sets of experiments where we considered 9 measures with exposure only, and this should be relevance. 9 measures with exposure and relevance. We considered different data sets, 6 in one case and 4 in the other, and different recommender models. So here we work with recommender systems, but you can think about ranking. So at the very end, what we evaluate are the ranking of items. So the first experiments we did was like we computed all the scores of these measures across different models and we looked at the score. What turned out is that some measures cannot even not be computed in the time. So entropy, for example, is defined for fairness as a result of many times the divisions by 0. This was actually a very easy case to fix. The other problem, as I anticipated, is that these measures, they don't have a specific range. So they all range in 0, 1, but it's not clear what is the minimum and maximum within this range. And what happens is that you can actually have a really broad range of scores. Some of them are very, very hard to interpret. So there are measures that give a score of 0.1, where in theory 1 would be the measure is the higher the better. And I think it's very unfair. The model is very unfair. But for another measure, you can get 0.6, same definition of fairness, which might think the model is moderately fair. So you cannot really look at the score of this measure as they are. And we could fix some of this with min-max normalization, but it's not possible for all of them. And then the other question we had was on the trade-off between relevance and fairness. So if we have these measures that consider exposure and relevance, do they really trade these two components? And what we found is the first model. It's not necessarily the worst in relevance. And the best model for fairness is not like necessary. And the best model for relevance is not the worst in fairness. So there is a kind of trade-off, but it's not always the case that if you increase fairness, the relevance has to decrease, which kind of is an implicit assumption out there in the literature. Again, we did some correlation analysis to see how these measures actually agree to each other. Here we compare measures only with exposure among each other. And what we realized is that they actually are highly correlated, apart from a few exceptions, while they tend to correlate much less with relevance measures. We did the same for measures that account for exposure and relevance. Somehow what we expected was that this measure could have this kind of trade-off between fairness and relevance, but turned out that this is not the case. So here correlations are very inconsistent. So there are some joint measures that correlate very well with relevance measures. So somehow they are more unbalanced towards relevance. And these are the measures that do not really correlate with fairness. So there is this kind of thing, either you are more towards relevance or more towards fairness. And then when I compare joint measures for measures that are based jointly on exposure and relevance, what happens is that somehow there are different groups. One where all the measures, so you can think about different clusters. Some of them correlate a bit more, some other they don't correlate. So the overall trend is a bit inconsistent. We also try to investigate this thing about looking at these measures if they can or cannot achieve the maximum possible value. So the question was, if I give them the first recommendation possible based on exposure, so I assign maximum exposure to all items in my dataset, can I really reach one? And again, here the answer was that so the circles are our corrected version. So by normalizing these measures properly, we could actually achieve one, so that the measure range is 0, 1. While these crosses, these are the original definitions, and you can see that depends on the measure. And sometimes, because of dependencies on the number of the cutoff, so the number of items that you actually show to the user in the web page, you can get some weird results with this measure, for example, really resulting in going down and up again. And we did ask the same question, but the other way around. So if we are in the most unfair scenario, can we actually reach 0? And again, you can see that with our measures, our corrections, we are here. There is a small exception there, and this is because of another limitations that we could, or it's not possible to resolve, to correct. And finally, we generated some synthetic data sets or rankings where we had a number of users and documents, and we increased the number slowly at each step. We increased the number of items that were exposed. So we started from the most unfair scenario and slowly increased towards reaching the most fair scenario. And we look at the behavior of these measures. So the expectation is that the more exposure, the higher the score of the measure. What we get is that some measures behave linearly. Some measure and kind of this is fine because these measures are the lower the better. So they are not linear, but they go down. There are some measures that are very strict. So, for example, this, if I remember correctly, is chain index. And what happens is it stays very close to 0 until you expose 90% of the items physically, and then it increases. There are some measures that have very, very weird behavior. So if you look here, this is again, the lower the better. If you look here, all the scores are squeezed. So the scale is very small. So these measures are very insensitive, basically. And then there's also a peak here, but again, in practice, these are very small scores. So, and again, this makes interpretation of these measures very hard. And we do the same for measuring the accounts for exposure and relevance. So here you have the behavior of relevance measure as comparison, and this is the behavior of fairness only exposure measures. So what we saw in the previous slide. And these are the measures for both for exposure and relevance. So again, you can see like these measures, there are some measures that behave linearly, but there are other things going on. And especially in this case, again, the range is very small, it's not a linear scale. And many measures are quite insensitive. So the more exposure and also the more relevance, the measure doesn't change so much. So to wrap up, if you really need to measure fairness, then the recommendation is to use that independently of relevance, because when you use these measures that account for exposure and relevance, you kind of get reliable scales and results that are hard to interpret. So if you really have to use these measures, then you need to be aware of the limitations. We also something worth to point out is that many of these measures need to be used only for relative fairness, comparison of two systems. And absolute fairness is not recommended, but if you have to do that, at least choose one of the measures you fix for the range, so that it's in 0, 1. And as a final conclusion about that, what we have seen today are two main topics. First one is how to measure when we have multiple dimensions, and the tone approach. And the second part was about fairness, and we had a look at some in fairness measures focused on individualized fairness and at the limitations they have. So future works, there is we need better measures, especially for fairness. So what kind of formal properties that we want from a fairness measure? So how do we define better measures for fairness, especially when we want to combine relevance with exposure? We also need guidelines for researchers on how to use these measures. And in general, what is missing now are measures that penalize systems when they retrieve harmful documents. And this is important both for misinformation, for example, but also for fairness. The key question is, how do we use these measures as effective functions for learning to rank? Because if they behave in such a weird way, what will happen when we optimize an algorithm for them? And how do we handle trade-offs for fairness stakeholders, for example? And how does this relate to bias? So if we have bias in data, does it mean that our system and evaluation should be unfair distribution of data and so on? So this was it. And thank you.
Questions?
There is a literature on topics that values like teaching decisions, such as very difficult different stuff. You know,
No, I don't. But it's something I can have.
You were trying to find somehow we can transition, to create this simple plan. Sometimes you just get so measures. I wonder whether these alternative characterizations will start by rather than looking for the best single organization. Can you characterize a few classes of different measures that somehow dominate the whole class? So, rather than picking a single, for instance, organization with respect to a lot of measures that show us, you say there are 2 or 3 out of a family, it's very large, that can actually dominate basically every other one reduces one of those. So you just create some sort of a summary of all possible scenarios and try to look for someone that's got the shortest possible measure. And of course, if the measure is not very short, then you have a problem. Because there are many possible words. Perhaps every single attempt to be rapid.
Yes. No, but this is something that it's kind of done for relevance when it's only relevance, because in IR we have different measures, and usually it's not just that we report one measure, but we consider a set of well-known measures. And some of them, it's known that they correlate. Some of them are a bit different, but yeah, this shows like a kind of what you were saying. Now, this is not the case for multi-aspect evaluation that is usually, and it's the same for fairness. It's usually one single measure because there is like traditional on this. It's less. All these studies are quite recent, right? So there is no like traditional. Yeah, but definitely it's the way to go.
Other questions? I have one. I mean, this is all beautiful theory, but how difficult is make it work for practitioners, for industry? I mean, if we speak of the 15 IR in six, they have problems in doing tests with normal non-mention aspect that people here there is a lot of sophistication. So is there any path towards exactly?
No. It is quite hard because there are many challenges already for, as you said, for a single aspect equation. But on the other side, like it's something that is needed. So it's not really like we can focus only on relevance going on. I guess now industry has also started to worry about these concerns, especially when it comes to fairness. But yet there is no like standard solution, and there is a lot out there because fairness has become very, very popular. But somehow there is no like among all these measures that we started for individual type of fairness, I would say that there are no really good measures. So the problem is still there. And one of the things we are actually trying to do and we are working on right now is try to define like a good measure for fairness evaluation, for example.
Thank you. Any other questions? Okay, so we are done with this idea.
A bit. Now we have just a bit of house cleaning for the course, ANOVAs, and other funny things. I don't know if you are keen on.